Vectors, no matter what they look like, they don't have to be standard vectors in R2, R3. If two vectors are orthogonal, the inner product is going to be 0, but also if the inner product is 0, the two vectors are orthogonal. It goes in both directions as it traditionally.
What's the difference between inner product and dot product?
Inner product is more like a generalization of dot product. When I use that phrase dot product, I'm really referring to vectors specifically in Rn.
Okay.
And then I look at the dot product, we talk about its significance geometrically, it describes the angle in between two vectors. But if I want to generalize what a dot product is, a standard kind of multiplication process on a vector space, I change the word to an inner product. Okay. It's sort of like saying, are two vectors in two space perpendicular? Does it mean the same thing that they're orthogonal? Yeah, I think so. I just have a tendency to use the word orthogonal when I'm in higher dimensional space. And to me, perpendicularity is something where we're restricted down to two-dimensional space. Sort of like dot products are restricted back down to Rn. Whereas more generalization into different vector spaces, I use the phrase inner product.
But they share the same properties, right?
They have the same properties. As a matter of fact, when I told you what the axes were for an inner product, I cheated. I actually went back into R2 first and talked about the characteristics of dot product.
Okay.
So I agree with that. And?
Well, I got a few here.
So we're in 4.
But yeah, 411.
By the way,
number 3.
it started out as a video game.
It did? Really?
Did it really?
Yes.
Oh, wow. I didn't realize that.
So back in number 3.
And then I actually have a couple from like a while ago, from like 4.7. Actually, I have a lot from 4.7. How many can I ask?
Well, point them out so maybe I'll take and shoot.
So there's a 4.7, 31, 33, 35, 29, and 25.
Because I think everything you have back in section 4.7 is just procedural.
Okay.
So maybe that might be something you and I go over outside of class.
One thing I was going to ask is these Legendre polynomials.
Legendre.
Legendre. All right. What is that? What's a Legendre polynomial and what's it used for?
It's huge.
It's huge.
Because when it comes to Legendre polynomials, relative to a certain product I can describe, an inner product, they really are orthogonal.
Okay.
And so Legendre polynomials are very important for that reason. And when you and I dive in, well, let me backtrack a minute. Hold that thought. So here's the x-axis. Here's the y-axis. So I think to talk about positions in two space, just from a math D perspective alone, nothing sophisticated, not math 33, I think life's difficult. I don't like this grid system because my axes aren't meeting each other already. So back in math D, it just kind of makes my life a lot easier when I force orthogonality with these two real number lines that I have to refer to as x and y axes, but they're just real number lines. And likewise, when it comes to functions, how about this one? And how about this one? I think, forget it, don't look at those. They're orthogonal. Jeepers. How about this? I think if I were to look at standard inner product in P3, taking a peek at my standard inner product and value in F1 and F2, I think the standard inner product gives me a value that's the standard inner product. You know, the homework you did last night.
It's going to be well, the quantity of x squared plus.
You guys.
All right, so x.
It's the product of the constant terms.
Yeah, I know. I'm trying to do math.
Plus the product of their coefficients for x. Plus the product of the coefficients for x squared. Plus the product of the coefficients for x cubed, which varies to positive 1. So relative to that inner product, I think those two vectors, those two functions, f1 and f2, are not orthogonal. Relative to the standard inner product. Now, when I messed up on the board before, when I think I had a g1 equals x squared plus x, and I think I said g2 of x was x cubed plus 1. Now, I think with the standard inner product in P3, those two vectors really are orthogonal. Their inner product values to 0. And so, if I want to force orthogonality, even with functions, even though it's much more goofy, it seems, than what we did in MACD with real number lines, still discuss orthogonality relative to another product.
Okay.
And those Legendre polynomials have that quality.
Good.
So what did you have in 411?
411 was, I think it was number 3, actually. I think it was kind of an early on one. I'll pull up here just a second. Yeah, number 3, 411.
You guys, did I mention
I didn't-
product in C? Yeah.
One of the things that I noticed is I just didn't get the same. Well, that looks like very straightforward, right? But I just didn't get the same answers back of the book, or the solutions, and I did it the same way I did all the other ones. So.
Then that too would be a prime example where I just need to look at your work individually.
Okay. Well,
Take it together. Michael?
Yeah, in 411, did you also go over number 19?
What's an inner product space? I asked, what's an inner product space? Yeah, a vector space where there is an inner product defined. Now, in this example, the specific inner product they gave you, let's see how you defined it. You defined it as, what number is this? He defined it as. Yeah, that's my point. He didn't define it. He's saying for any inner product space, is the evaluation of this particular mess right here going to be 0 necessarily? Without identifying what the inner product is in terms of this mechanism, how it operates on 2 vectors, I think we can prove it just using our axioms. And in using our axioms, I don't know, does anybody have an idea? How about this?
are they referring to the axioms? Well, I guess they call them propositions in this chapter, or the actual axioms in chapter 4 for vector space?
I think we're talking about the
No.
proposition for inner space.
Are we talking about the propositions for inner space? Because they don't refer to those as axioms. Yeah, they refer to them as propositions.
It's like the mapping.
Or properties, yes, properties, not propositions. I need to stop abbreviating to prop.
I see your point. I mean, I would still refer to these as the axioms I have to satisfy to have an inner product space, and the author's using the same language I am.
Is there a difference between axioms and properties, or are they just the same thing, just synonyms?
No, I don't think in general I would necessarily interchange those 2 words.
Okay.
Because I think properties is more general.
Okay.
It's simply a characteristic some system has in mathematics. Axioms are different. Those are like a checklist I mark off to see whether or not I satisfy some definition, whether it's the actions defining a vector space or actions defining an inner product or whatever you might have.
Okay.
And so I think the word axiom is more stringent. It's really the basis for a whole system in mathematics.
Okay.
You guys look at geometry? A geometry has its own set of axioms. Euclidean geometry specifically has 5 axioms of standard we refer to. And algebra is another mathematical system that has its own axioms. A calculus is simply a system that has its properties. And so I'm just referring to the axioms of a specific inner product space here. Even the author, when you read question number 19, if you don't have your book, let me read the instructions.
He refers to them as axioms there.
Good, that's what I was pointing out. Prove from the inner product axioms that in any inner product space V, that this evaluation is going to be 0. So you guys, check this out.
But they refer to them as properties in the definition. 4.11.10.
So 4.11.3.
4.11.10.
Point 10.
Yeah.
Sorry, I'm in the wrong place.
did I pull up the wrong one? There's another one here, but they still refer to it as properties in 4.11.3 as well.
Okay, yeah, he says we use properties 1 through 4 as a basic defining properties of an inner product space. Okay, he's using those words interchangeably here,
Okay.
but I think they're always interchangeable.
Okay.
So you guys can give it a shot. What do you think? So like listen.
Yep. Well,
Are you saying I'm doing something wrong?
well, it's v times v. You're multiplying v by the zero vector.
No, it's a zero, it's a,
Also, you don't know
multiply
that
by
it's
each
a
other.
zero vector.
What's
Okay.
that?
You don't know that it's 0, zero is a zero vector.
Perfect.
Yeah.
Not only do I not know that, I do not know that my vector space is Rn. And number 3, I'm wrong for another reason. It may not be a standard inner product definition. Do you guys see my point?
Yeah.
I'm being way too specific here. So let's see if you and I can't verify this is equal to this, but just using our properties of inner products so that we don't have to specifically identify what the inner product is. Do you guys agree with this? Isn't 0 bar 0 times something? Because 0 magnitude.
Mhm.
So can I pull a 0 up front? What do you think?
Can you do that?
You know it's legal, I just don't think it's using the properties or axioms
Yeah.
of the product space. I can't just pull out a coefficient out of the second entry. Actually, when you look at the axioms for inner product, doesn't it say that I pull a constant out of the first entry? Oh shoot, so I made a mistake. I guess really to prove the statement's true, use my axioms, no tricks this time. I better first
Rewrite v 0.
thank you, interchange, because that's one of our axioms. We have commutativity holding for us with this inner product. It's just that I really can think of 0 bar as 0 times it, could I not? But now that I got the first vector as itself times some scalar, that one of the axioms, I forget which number, 3 or 4, allows me to pull out those coefficients from the first component. Now, what inner product am I really dealing with? I don't know. I don't care, because 0 times anything, it's just 0. It's more of a trick question, just making sure you're binding your P's and Q's, using exactly what the identity is telling you to do.
So why can you pull out a 0 from the 0 vector? I think you said something about magnitude.
Well, I was merely suggesting that its magnitude is 0. And so taking a vector, rewriting it as itself times, well, a unit vector times its magnitude, I'm misspeaking. I shouldn't say unit vector. It's just such a special vector. I think you can interpret it as 0 times itself. And that's true no matter what 0 bar looks like.
So what about the other axioms?
What about them?
Do we even have to look at them, or since we found that I equals 0?
No, I'm just simply trying to verify with the axioms that this is a true statement, and I have. So,
Okay.
so be it, I didn't use all my axioms.
So you only have to, if you prove that it's true with one axiom, you don't have to use the other ones?
Oh, sure, he never said you have to use all of them.
Okay.
And I admit, you have to admit, I did use 2 of them. Commutativity and
Okay.
pulling out a scalar from the first component.
Okay.
Well, you guys, do this for me, from your background. Let's go back to trig. So, if I consider a vector, how about v1 bar, and another vector v2 bar. Oh, it's too big. Just a minute. And I were to consider a scalar projection of, in this case, v2 bar on the v1 bar. Wouldn't a scalar projection merely be this? Let's see, flashing a light above this chip in such a way that the rays of light are hitting the vector v1 bar at a right angle. Then I think the length of this green line segment is what I'm going to interpret as nothing more than a scalar projection of my vector v2 bar on the v1 bar. You guys, am I getting too sloppy already? I said v2 bar on the v1 bar. Now, for you and I to talk about the evaluation of the scalar, let's play a simple trigonometry game. I got a right triangle. Let's talk about the angle in between V1 bar and V2 bar. Would you guys not agree in my picture that if I plant my feet at the vertex where V1 bar and V2 bar meet, is it not merely true that the cosine of the angle theta is nothing more than the ratio of, gosh, what does that look like? Is that a V1 bar in terms of magnitude on the V2 bar? Just using my right triangle definitions. You guys just don't want to play. What do you mean no?
No.
Why are you saying no?
Because that's just not it. It's going to be,
What do you want to change to make it a true statement?
well, you need to make sure that your cosine of theta, your theta is pi over 2, right? In this situation, and then, well, you could check that out, but you need to check that out by taking the dot product on the other side.
I know I can do that. I want you guys to deal with my mathematical statement. Are you saying it's not true?
Yeah.
It's not,
No.
Well, the V1 goes over the
Thank you.
projection, so
Yeah.
it's not.
I think when it comes to my numerator, it does not really link to the adjacent side of theta. All right, I'll fix my mistake. I guess what I really want upstairs is nothing more than the green thing, the scalar projection of V2 bar on the V1 bar. Do you guys agree? And that being the case, I think my scalar projection of V2 bar on the V1 bar could be interpreted as nothing more than the magnitude of V2 bar times the cosine of theta. By the way, you guys, I'm still not talking math 33, I'm talking math 8. Shoot, you know what? I don't like this. I don't like, because I like to see the dot product in here. And I think I can force the issue. I think the scalar projection of V2 bar on the V1 bar could be interpreted as the magnitude of V1 bar times the magnitude of V2 bar times the cosine of the angle in between. Actually, that's not legal, is it? I guess I can't just multiply something by V1 bar's magnitude, but I can if I compensate. And why would I want to do this? So that when you take a peek at what's on the right-hand side, you can interpret in terms of the dot product. I think the scalar projection of V2 bar on the V1 bar could be interpreted as the dot product between V1 bar and V2 bar, all over the magnitude of V1 bar. But you guys got to confess, what's sitting on the board on the right-hand side of my equal sign, you have to confess that is merely a number. It's the length of that green line segment. So can I change it? Now let me talk about this vector. Matter of fact, it's so important. Can't give it a name. I'll call it how about U1 bar? That being the case, I think of my picture. All I have to do is take the scalar and multiply it by a vector. And I will generate the projection of V2 bar on the V1 bar as a vector, and I'm simply going to multiply it by V1 bar. You guys, is that okay? Michael?
Why is the magnitude on the bottom just A by itself? Is that from dotting V1 and V2? Or?
Not really. It's more from this. You have to confess, this is a simple statement just coming from my right triangle trigonometry. I cleared fractions. At this point, Michael, I just was trying to force myself to see a dot product. I don't. But if I just insert a factor of V1 bar's magnitude upstairs, that is a dot product. So I multiply by V1 bar's magnitude. It's just not legal, so I divide it out by it. So that in the end, this is just a funky looking form of 1 that I multiply to the right-hand side of the previous equation. So this really came from my forcing that factor to be a factor in the numerator's position. You guys, I think I'm wrong. I think I'm really wrong. If I want a vector projection, which really is that green vector, I don't want to change its magnitude. This is its magnitude. So I'm going to take this magnitude and multiply it by a vector going in the same direction as V1 bar, but whose magnitude is 1. Piece of cake, I'll simply come in and divide out by V1 bar's magnitude. So that in the end, the vector projection of V2 bar on the V1 bar is nothing more than the dot product of V1 bar with V2 bar. over V1 bar's magnitude twice times V1 bar. How am I doing so far? Okay, because I want you to tap me. Because I think I can generalize this and not worry about dot product, but just look at a standard inner product. It's going to give you the same result. Oh, you know what, guys? I want to do something else. Let's talk about with my blue pen. This vector right here. I want to force this vector W bar to exist in such a way that it's orthogonal to V1 bar and U1 bar. And I want it orthogonal to this vector slide over here. I think this is an equivalent vector. But would you guys not agree that U1 bar plus W bar is equal to, I don't know, what is that equal to? V2 bar. Or shall I say it differently? I think W bar is equal to V2 bar minus U1 bar. And if you guys don't mind, I'm going to give it a whole new name. I'm going to call it U2 bar. So U2 bar is going to be nothing more than V2 bar minus this projection of V2 bar onto V1 bar, which, by the way, look at my notation over here, is going to be nothing more than the inner product of, in this case, my U1 bar with the V1 bar. Or did I say V2? All over. I can't remember writing. This is going to be nothing more than simply rewriting this using inner products. Is that V1 bar dotted with V2 bar? Is that over V1 bar's magnitude twice times V1 bar? You guys, can I restate? Yes.
Sorry to get off topic. But you're in trouble, Mr. Valguy.
Why?
You told me that there would be no vector calculus in this class. At the beginning or in the middle of last semester.
This is Math 32
that's
right
true.
here.
But I have to admit, if I use that phrase vector calculus, it's more like I'm differentiating and integrating with vector value functions. And you got to confess, I'm not applying any of the calculus tools in this particular discussion.
Okay.
All I'm really looking at is vectors, period.
Okay,
But this
sorry.
really is something
There's
that
quite a amount
we
of
learn in
I just
32.
remember you telling
Right.
me, you're not going to be using much from Math 32.
Yeah, and I really am not. To me, vector valued functions are really interesting when you start talking about a curve in 3-space or higher dimensional space. I mean, for those of you who have not seen multivariable calculus, how many of you have taken Math 32? Oh, vast majority. There's still several who haven't. You know, if you're going to talk about a curve in 3-space, it's difficult mathematically, unless you do something like this. Consider a bunch of vectors emanating from the origin whose tips are tracing out that curve. So vector valued functions are fundamentally important if you want to talk about multivariable calculus. That's why in our typical Math 32 course, we discuss it so heavily, because we're jumping into higher dimensional space. But again, you guys got to confess, I'm being a little silly today. No calculus, I'm just messing with vectors. And I think if I were to generalize this, generalize, I think I could say this. In my picture, let U1 bar be V1 bar. And I'm going to choose U2 bar to be nothing more than what I have down here. So allow me to write. I think it's nothing more. Then my V2 bar minus the projection of V2 bar onto V1 bar, which is the same as U1 bar, all over U1 bar's magnitude twice times my U1 bar. And in this fashion, my U1 bar and U2 bar will be vectors that are orthogonal to each other.
Okay, so this is just some case where U1 bar is equal to V1 bar.
Yeah, the first case is really easy. I'll just set them equal to each other. Now, don't take it the wrong way. Because I think I didn't fill in enough details. I'm not suggesting in my picture V1 bar and U1 bar are the same. I'm suggesting this. If I got a collection of two vectors, V1 bar and V2 bar, and I want to force orthogonality, I'll choose U1 bar to be V1 bar. But my U2 bar is going to be nothing more than the second vector V2 bar minus a projection of V2 bar onto U1 bar. So what I'm really trying to do is create two vectors that are orthogonal to each other. They may not have a specific magnitude that I might want. I might want to force them to be unit vectors. We'll get there. For now, I'm just talking about a procedure for which I can force orthogonality for base vectors in a vector space. Nothing more. Actually, what I have in black on the board is so important. Can I give it a name? I'm going to call this my... Oh, shoot. Okay, now I'm embarrassing myself. I don't know if I remember how to spell it. Gram-Schmidt?
So what does orthonormal mean? Is that what you've just done there?
Now, sometimes when I create the system of vectors, the U1 bar and U2 bar, which are perpendicular to each other, or orthogonal to each other,
Yeah.
sometimes I want a stronger requirement that they be unit vectors. That being the case, I'd be creating a set of orthonormal vectors, as opposed to just a set of orthogonal vectors like I have in this case.
Okay.
It's easy to do. If you want to create a set of orthonormal vectors that span the same space as V1 bar and V2 bar, it's this easy. You're just going to take your U1 bar and divide out by its magnitude. You're going to take your U2 bar, divide out by its magnitude. That'll be a set of two vectors that are not only orthogonal to each other, but they're unit vectors. I'll consider an orthonormal set of vectors. It's just a fancy word describing those two qualities.
Okay.
It's be there. Now, if I had two vectors, I misspoke, sorry. If I have three vectors, V1 bar, V2 bar, and V3 bar, and I want to force orthogonality, I don't change my procedure. There it is. It's just that since I had another vector, V3 bar, I'm going to assign to U3 bar nothing more than V3 bar, minus its projection onto U1 bar. And minus its projection onto U2 bar. Can I change this? What if I had n vectors, v1 bar through vn bar? Then I think my u sub n bar is going to be nothing more than v sub n bar. Minus, oh, you guys, it's too much writing. Can we change it? What's your favorite Greek letter?
Delta.
Yeah, I thought so. So subtracting off a sum of these things are referred to as the projection of my v sub n bar onto u sub bar sub what is 9? All over u sub I bar's magnitude twice times u sub I bar. As I ranges from to minus 1. Good. You guys, I'm being silly. I'm just saying it's a generalization. By the way, this procedure might not be that straightforward. You've got to worry about what your definition of an inner product is. Keep that in mind. So, do you guys think we're ready for an example? So you guys, I just grabbed an arbitrary two vectors from P2. They actually form a subspace of P2. I want you to create a whole other basis for the same subspace as the space that B spans, but with a set of orthogonal vectors, and using the Gram-Schmidt procedure. So if you allow me to refer to this piece right here as P1, this piece right here is P2, I'm really trying to create a set of vectors Q1 and Q2. Where? I think to make my life easy. I'll start out by letting Q1 be P1. In other words, Q1 is going to be nothing more than my x squared minus 2. However, my Q sub 2 is going to end up being my P sub 2 minus the inner product of P2
So
and Q1.
Is it a good idea to name your variables the same thing as your vector space?
I mean, well, shoot. No. Because I think when it comes to this vector space,
Yeah.
I mean, it's maybe it's just a habit perhaps. I have a tendency to use the letters closer to the beginning of the alphabet,
Yeah.
which I think it has nothing to do with the name of the vector space. Now, I know this vector space is, or excuse me, I'm coming from P2 as a vector space.
You referred to one of your elements as P2 as well.
Yeah, P1s and P2s. I don't know, it's just a habit, a convention I have.
Okay.
And I admit they coincide here, but they don't have to.
Okay.
Look at this vector space. Continuous functions. Don't I typically refer to those as F1s and F2s, or Y1s and Y2s?
Yeah.
Can you just explain one more time why you set Q sub 1 equal to P sub 1?
Yes, I can. But think about it. Watch. Look at this picture. Don't look at the details. If I got two black vectors here that are not orthogonal, and I want to create a basis for the same vector space for which these two are base elements, why not just start with one and get perpendicular to it? And so I'm just starting somewhere. And so when I ask you to use the Gram-Schmidt procedure, I'm expecting you to allow the very first new vector, U1 bar, or excuse me, in this case Q1, to be the same thing as V1 bar, or in this case P1. However, I think there's a bit of work generating the second one. So you guys, let's dive into the work. And diving into the work, does that give me, shoot, I made these up out of thin air. What's P2? So X plus 1. Minus, oh, by the way, I'm doing a lousy job with these examples, you guys. I meant to say, can we assume the standard inner product in P2? I didn't say that, but that's what I meant. So, please help me with this. What's the numerous position? Oh, Jesus.
Two.
Negative 2. And I think in the denominator's position is square root of, you guys.
1 plus 4, 5.
Thank you.
5. Yeah.
And I'm going to square it. And I'm multiplying that by my Q1, which is nothing more than X squared minus 2. All right, so I've got bad word management issues today. That means Q2 could be interpreted as my X plus, is that a plus 2/5 times X squared minus 2? Or shall I say I've got a 2/5 X squared, is that a plus 1X and plus 1/5? You know what, you guys, maybe I shouldn't have done this. I'm the one who made the example up out of thin air. Maybe I already had orthogonality between these two vectors of P2. I said, maybe I already had orthogonality with these two vectors of P2. I can say that.
Maybe you have to or take the dot product and see if it equals 0.
And
Or
what
inner
is the inner
product.
product value of these two
That'd be 1.
functions?
It just looks so
It's
weird
negative.
writing it out.
It's
like
not
that.
0, so they're not orthogonal.
Yeah.
Oh, maybe I made a mistake. Maybe this set of Q1 and Q2 is a set of vectors that are not orthogonal. Let's check. Here's the first. Here's the second. That being the case, I guess, I don't know, let's check it out. Coefficient of x squared times the coefficient of x squared is 2/5. Plus the coefficient of x times coefficient of x is
-2.
0.
Oh, 0, yeah.
Plus constant times constant is
2/5, negative 2/5.
Oh, so 2/5 minus 2/5, it works, is equal to 0. So I think these two vectors, these two elements of the vector space P2 are indeed orthogonal relative to my standard inner product on P2. Do you guys agree?
Yes. So all you're doing with the Gram-Schmidt is just forcing orthogonality.
I'm forcing orthogonality.
Okay.
I also might say in English, this is a set of orthogonal vectors that
What-
spans the same subspace as the set B does.
What if the function doesn't want to be orthogonal?
I'm
You're making it
forcing
do it against
orthogonality.
its will? I mean, that's
I'm
neat.
forcing it.
All right.
Oh, by the way, shoot, I'm really not on the ball today, I'm sorry. This may be an orthogonal set of vectors, spanning the same space that B does. But what about an orthonormal set? What would that look like?
You divide each by their magnitude. So you would have x squared plus, or minus 2 all over root 5, yeah. And the next one is whatever the magnitude of that
Yikes,
is.
hold it. Oh, come on, isn't that nice? Jeepers. All right. How's my arithmetic?
I don't know about your arithmetic, but right here, that's square root of 5. I'm having trouble seeing where that's coming from.
Well, that came from the magnitude of this vector right here. And I think the magnitude of the vector is going to be nothing more than, anybody? Square root of its
Its components.
inner product of itself. But since I'm dealing with a standard inner product, wouldn't that be the coefficient of x squared times itself twice? Plus the constant term times itself twice. And that's where I got it.
So are you ever going to want us to graph any of these or do anything like that, or if we just know the procedure, if that's good enough?
Oh, don't worry. By the next exam, we'll be graphing some of these.
Okay.
My whole issue is this. I want a yes or no answer. Is that a, well, you tell me what that is.
It's an ellipse.
I agree. What about something like this?
It's a parabola.
It's a shifted, no.
It's not shifted, but it's a rotated
Rotated,
conic
yeah,
section.
yeah.
And for you and I to rotate these conic sections, you and I are going to be doing just this. We'll create a, here's the x and y axis. We'll create a whole new x prime and a y prime axis, in which we can graph a more standard ellipse or hyperbola, parabola, whatever it is, in that rotated space. And so we'll be graphing things like that in the near future.
Okay.
Oh, you guys, my example's too
Easy,
yeah, so can I raise the level of intensity?
if you must.
I'm stalling you guys because I need to identify exactly what these elements look like. Unless you and I define an inner product in the following fashion. The inner product with P1 and P2 will be the sum of I times P sub I, Q sub I, hold it, I meant A sub I, jeepers, B sub I. As I range from, 1 to 3, but I'm going to change the coefficient. You guys, sorry for stumbling in this example. When I had just an I in there before, that would not generate an inner product. It would fail one of the axioms, the first one. So I had to change it. All right, that makes more sense. Now consider this set of vectors. Use the Gram-Schmidt procedure. To generate. another set of orthogonal vectors. That spans the same space. So you guys, my instructions clear enough? And by the way, I did a lousy job with my board space. Can I erase it?
Sure.
Actually, no, I'll leave it as such. I'll jump over here. And I maintain my whole new vector. I'll call these vectors Q1, Q2, and Q3. And I'll think of this as P1, P2, and P3 if that's okay.